One, from the Bohr model, we only had the principal quantum number n. But we saw that when it came to de Broglie and Schrodinger, those who came up with quantum mechanics, they observed that electrons, even within the same principal quantum numbers, are not similar and occupy specific spaces within those principal quantum levels, where you have probability of getting electrons. I hope you can hear me, although there is rain on the background. Can you?
Yes.
Yes.
Yeah. So today I wanted us to look at the different ways of looking at quantum numbers. Now, when you are looking at quantum chemistry, we say that within a principal quantum level, that is n, and n principal quantum levels are given numbers 1, 2, 3, 4 upwards as you move away from the nucleus. They are what we call sub-levels, isn't it?
Yes.
So we are talking about one, we have a principal quantum number, n, which is given numbers 1, 2, 3, 4, right? Upwards, right?
Yes.
We see that there are some sub-levels where electrons occupy specific sub-levels within those principal quantum numbers. And we name them as, those ones we used alphabets. The sub-levels we named as
SP, D, and F. D and F.
Yeah, correct. Now, in terms of when we are, so those are the descriptions that we give to sub-levels. But in terms of quantum numbers, those sub-levels are given numbers 0 upwards. So that S is given number 0. Can you read my screen where they are labeled?
Yes.
Yes. E is given number 1. E is given number 2. F is given number 3. You can have now others, G and H, but on ground levels, usually we go up to F. So as you can see here on my table, then those sublevels are described by letter L, and they take the numbers 0, 1, 2 upwards, where 0 represents S, 1 represents P, 2 represents D, 3 represents F. P is 3. As just like the way we say S, P, D, F, you start from 0, 1, 2, 3. Together.
Yes.
Yes.
Now, where you have sub-level, in those sub-levels, you have, for example, when we were looking at, apart from S, when we were looking at, for example, P, sub-level P, we saw that we can have PX, PY, and PZ, right?
Yes.
Now, those are orbitals, isn't it? So within sub-levels, we have orbitals, right?
Yes.
Now, the orbitals are represented in terms of quantum numbers by ML. So just a minute. So, sorry for the moment. Can you hear me?
Yes.
Yes.
So, we are saying
Yes, Doctor.
now,
Yeah, hear you.
you know, those every sub-level. Now, every sub-level has orbitals. Now, the orbitals are represented by ML. And the orbitals take the values from negative L to positive L. For example, if the sublevel is 0, then there is only one sublevel orbital, because negative 0 and positive 0 are the same, isn't it?
Yes.
Yes.
So we have said that R is equals to 0 is the S sublevel, isn't it?
Yes.
So the S sublevel has only one orbital, 0, which is now the S sublevel. Now, which is the orbital in the S. There's only one orbital in S. Now, when you go to P, it is take the value of 2, isn't it? Of 1, right?
1.
P is 1, right?
Yes.
So it has how many orbitals? It will have as an orbital negative 1, 0, up to 1. Are we together? So that is why there are 3, Px, Py, and Pz, right?
Yes.
So if we go to D, which takes a value of 2, L is equals to 2, then what will be the values of the orbitals in D?
0 and 1.
Now D is 2. And we think that the values of orbitals are from negative L through 0 to L. So what will be the values?
It is negative.
Negative.
Negative 0 to 0.
Now
0
D is
and 0.
number 2. So what will be the values?
Negative 2 and 0.
Negative 2. Yeah.
Negative 2, negative 1, 0, 1 and 2.
Yeah, negative 2, negative 1, 0,
0, 1 and 2.
1 and 2. Those are how many?
5.
5. That is why in the D orbital has 5. The D sublevel has 5 orbitals. You saw that. And that is why it carries 10 electrons, isn't it?
Yes.
So if we go to F, because those are the ones that exist naturally, it will take the value of so F takes the value of what? 3, isn't it?
Yes.
So what are the possible, what are the orbitals in F?
Negative 3, negative 2, negative 1, 0, 1, 2, and 3.
Correct. So those are how many?
Yeah, 7.
They are 7. So that is why the F sublevel has 7 orbitals carrying a maximum of 14 electrons. You get it? So there is a relationship. Now we are creating a relationship between N, R, M, L. Can you now see the mathematical relationship?
Yes.
So
Yes.
N is equals to 1. The possible sublevel is N minus 1, which is 0. And that is the S orbital. If N is equals to 2, the possible sublevels are up to 2 minus 1, that is 1, and that means 0 and 1, because sublevels start from 0 up to the N minus 1, and that is S and P. n is equals to 3, that is principal quantum shell number 3, you can only have sublevels up to 3 minus 1, which is 2. That means 0, 1, and 2. Now, for a sublevel for a sublevel L, the possible orbitals ML are from minus L to positive L, counting all the integers. Are you together?
Yes.
Yes.
So we have a principal quantum level, which is related to the sublevel L, and the orbitals ML. Then within an orbital, there are 2 electrons, right?
Yes.
One which must have opposite spins, clockwise and anti-clockwise, and each is given the value of a half, either negative half or positive half. So that is why we say that Pauli's exclusive principle says that no 2 electrons within the same atom and have all the 4 principal quantum numbers, and now have all the 4 quantum numbers being the same, because you may have the same n, you may have the same L, you may have the same ML, but then there will be a difference in MS, the spin quantum number. So N is the principal quantum number, L is the orbital quantum number, ML is the magnetic quantum number, and it is the one that gives you the dimension of an orbital. And that is the orbital quantum number, the magnetic quantum number. And MS is the spin quantum number. So I hope that one is clear, right? So
No.
So you want me to repeat?
Yes, please.
Yes, pardon. Sir.
Okay, let me redo. So when it comes to the principal quantum number, that one you understand, isn't it? That the numbers are counted from the one nearest the nucleus out as you go out, right?
Yes.
And that is why we are saying that they determine the size of an orbital. So the one that is lowest is 1, then 2, then 3, n. So the n, those are the values of n. Now, when it comes to the sublevel, which we are calling the orbital quantum numbers, those are sublevels, the numbers that represent sublevels, they take the values from 0 up to n minus 1. So if I tell you that we are dealing with principal quantum shell number 1, we can only have a sublevel n minus 1, which is a sublevel
S.
S, which is 0, right? S is the
Yes.
one with value 0. If, for example, we go to principal quantum shell number 2, it can have sublevels from 0 up to 2 minus 1, which is 2 minus 1 is 1. So it is only 0 and 1, isn't it?
Yes.
0 representing S and 1 representing
P.
P, correct?
P.
Is correct. So if we go to n is equals to 3, what are the possible sublevels? It is from 0 to
2.
2, which comes from 3 minus 1, right?
Yes.
Yes.
So the
Yes.
possible sublevels are 0, 1, and 2, right?
2
Yeah. So 0
and 2.
representing S, 1 representing P,
P.
and 2 representing
D.
D.
Yeah. And now the one that is given here is up to 4. If you go to principal quantum cell number 4, the possible sublevels are
0.
0,
0,
1,
1, 2,
2,
2 and 3.
and 3. So that is in the principal quantum shell number 4, we can have the sublevels 0, which represents
S.
S, the sublevel 1, which represents
P,
P.
the sublevel 2, which represents
D,
P.
and the sublevel 3, which represents
3, 4.
F.
F, correct.
F.
So now that one you understand up to there, isn't it?
Yes.
Now, so the sublevels are the ones that represented them by the principal, by the symbol L, right? And L represents what in quantum terms is referred to as orbital quantum number. Now, within sublevels, we have, that is where sublevels are the ones that hold orbitals. And we say that orbitals are the spaces where electrons reside, right?
Yes.
And those orbitals are represented by ML, which in quantum terms is referred to as the magnetic quantum number. And ML can take values relative to the L, which we are dealing with. You know, ML is within L, isn't it?
Yes.
If L and ML takes the values of L from minus L up to positive L, right? Or the integers. So if L is 0, what are the possible values of ML?
0.
1.
It's only
0.
there's only one ML, which is 0, right? The value is 0, right? And that is there's only one orbital. So if L is equals to 1, and that is when you're talking about the p orbital, what are the possible values of ML?
Minus 1, 0, and 1.
Minus 1, 0, and 1, meaning that
0.
P has 3 orbitals, minus 1, 0, and
1.
1. So if L is equals to 2, meaning we are talking about D, what are the possible orbitals?
-2, -1, 0, 1, and 2.
Yeah, those are 5, and that is why D orbital has 5, right?
Yeah.
Yes.
If L is equals to 3, what are the possible sublevels?
-3, -2, -1, 0, 1, 3.
1, 2, and
3. So those are how many?
7.
7. And that is why the F sublevel has 7 possible orbitals, right?
Yeah.
Yes.
And of course, you know that each orbital can hold a maximum of 2 electrons, isn't it?
Yeah.
So if you want to know the number of electrons, you multiply the orbitals times 2. Is that clear?
Yes.
Yes,
So for whatever orbital you are talking about, it can hold 2 electrons, right?
Yes.
Even the last orbital.
Yes. You know, within a sublevel, there are orbitals. An orbital is a space that can hold 2 electrons.
Okay.
These are ML. The MLs are the orbitals. Each of those can hold 2 electrons. So those 2 electrons must have opposing spins. If one is spinning clockwise, the other one must spin anti-clockwise, right?
Yeah.
So if we give one a value of -0.5, the other one will take a value of
Positive.
Half.
So basically, those are the 4 possible quantum numbers: the principal quantum number, orbital quantum number, which simply we call the sublevel, the magnetic quantum number, which represents the orbitals, and the spin quantum number, which indicates the direction of an electron spin. Is it now clear?
Yes.
Yes.
So
Yes.
you can check. These are
Somehow
here, what I'm
it's
portraying, I'm displaying here is directly from you can refer to this. I just wanted to clarify that before we now go back to periodic table. So now I am going to display the periodic table. We are going to look at threads.
Yes.
You can be able to read my screen.
Yeah.
Yes.
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 Igochore.
Now, that is the threads, periodic threads of chemical and chemical. So there's some background noise. So somebody need to. Yes. Threads and the periodic table. So what are the threads that run across the periodic table? Now, there are more than 20 properties that change in a predictable way. That is, you can say that, a periodic table, we say, is a table where we place elements by representing them with their symbols. In a table that consists of rows and columns. Rows represent periods from row 1 to row 7 for the known elements.
Tuko pamoja?
Yes? Can you hear me?
Sorry?
Can you hear me?
Yes.
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 Please start, Daktari, about that.
Yes? So, some of the properties that you can...
You start about so that
Yes?
we can hear you clearly.
So some of... when
I'm saying
yes?
you can start so that clearly.
I'm not getting you clearly.
I was requesting that you start and about the trends.
So that is where I'm starting about trends. Trends across groups and periods.
Okay.
And we are talking about the
It's
periodic table.
okay now.
Yeah. So we are saying that
Okay.
there are many threads that we can look at. You have to look at a certain character of an atom or of elements that can be compared to its position in the periodic table. Those are the threads we are talking about. And there are different threads that are predictable. You know, a thread is something that is a characteristic where changes in a certain characteristic happen in a certain way, in a predictable way. So the predictable threads that can be studied can include density, melting point and boiling point, atomic radius, ionization energy, electronegativity. Mostly the threads I'm going to look at today are atomic radius, ionization energy, electronegativity. And when we are looking at ionization energy and electronegativity, before we do that, we shall look at threads in terms of whether elements in a certain group period form positive ions or negative ions, the possibility, the ease with which they form those ions. Those are the type of threads we'll be looking at. So if we go to, let me first of all try to bring the periodic table. So basically the periodic table is like this, right?
Yes.
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 Although let me give the periodic table that we are used to. Let me see, generally up to period 5. This is the periodic table, right?
Yes.
So again, just for reminder purposes, each column represents a group, right?
Yes.
If we have include up to the d orbital, then those, usually those elements with an f orbital are placed outside the normal periodic table. Sorry. From column 1 to 18. However, when we are in the normal periodic table, usually those in the D are considered differently. So usually we consider column 1, column 2, then we jump the 10 elements in the D. We go to column 3, 4, 5, up to 8. And that is what we call groups 1A. Groups A. So groups, elements in group A, or in groups A, in the group of category A, from 1A up to 8A. But now here we are not, so that those in the middle are in the B. But here we have put all the elements up, including D. And so that is why we have up to 18 groups. Because, if you count from S has 2 electrons, P has 6, that comes to 8. D has 10, that gives you up to, so S2, P6, 8, and D10. So that gives you a total of 18 possible elements that can hold those 3 sublevels. Now let me go back. So we look at threads generally. Now, looking at group 1, although you can ignore hydrogen, per se, when you're talking about group 1 elements, you don't talk about hydrogen, although we can temporarily hold it there. Otherwise, the elements in group 1, okay, hydrogen fits in the sense that it has one outermost electron, and that is the characteristic of group 1. But hydrogen and helium usually are considered separate. So we can consider group 1
Is
from
Mwalimu
lithium
on really?
Francium, right? So from lithium up to down to francium, that is those are the elements that hold group 1. Now, what is the similarity? And the reason why we have included hydrogen is that in this sense it has that similarity, that the outermost principal quantum level has only one electron. Can you see that?
Yes.
That is what, because you can see that hydrogen has only one orbital and it has one electron. Lithium has 2 orbitals and the outermost electron is 1. Sodium has 3 orbitals, one with 2 electrons, one with 8, and the last one with 8. So the similarity is a single electron in the outermost shell. So what is changing as you move down the group? Because this is a movement down the group.
Atomic number of
The number of principal quantum
Energy
levels.
level.
Yeah, the number
Energy
of
level.
energy levels is increasing as you go down the group, meaning that the distance of the outermost electron from the nucleus is moving further and further away, right?
Yes.
So basically, the distance from the nucleus to the outermost electron is what we call the atomic radius. So atomic radius is basically presumed to be the distance from the nucleus to the outermost electron. Now, practically, in practical terms, that determination is very difficult. So that determination is very difficult. So usually, the determination of an atomic radius is that now we are talking about practically, in practical terms, is done by either considering atoms that of elements that are in molecules, taking them, and what can be determined physically is the distance either from the nucleus of one atom to the nucleus of another atom for molecules that have joined together into a molecule. For example, elements like fluorine, chlorine, oxygen, they exist as diatomic molecules, isn't it?
Yes.
So for those, you can, using X-ray techniques, it is possible, electronic X-ray techniques, it is possible to determine the distance from one nucleus to the other for those molecules. Now, when you determine that distance, if you divide it by 2, then it will give you the distance from the nucleus to the outermost electron. It is half the distance between the 2 nuclei, right? So if you determine the distance between the 2 nuclei, then you divide by 2. That is the atomic radius. Now, that is for molecular elements. Now, for ionic elements, for example, metals, that can only be determined by taking the metals in their crystalline form. That is where, when they are in the solid form, it is possible to use X-ray techniques to determine the distance between the nucleus of 2 atoms that are bordering one another, and then you divide by 2. There's somebody who should mute. There's somebody who they are getting some background noise. think person has muted themselves. So, and Sylvester, you are raising your hand.
Yes, Daktari, I wanted to kindly request, I've
Yes.
got lost. I've got lost from the point where you had displayed the periodic table
Yes.
and you were talking about the groups.
Yes.
I lost you from there. I couldn't hear you until such a point, until this point now. So I'm requesting kindly you revisit just briefly so that I can move with you closely.
Okay. 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 Just a moment.
Yeah.
I had gone to another level. I was portraying this simple periodic table. You know, a normal periodic table, of course, is more complex. This one is just a simplistic representation of periodic table. Now, usually, this is how the periodic table is usually represented, although at the bottom, there are some other elements that have the F level. So these ones are those up to 14. They are the ones that are usually placed up to the D sub level. These are the ones that are usually placed in the main periodic table, right?
Yes.
Yes.
And probably let me go to the usual periodic table, the way it is represented. Just hold on, so that probably I not need to. This is now usually how you get your periodic table, isn't it?
Yes.
Yes.
So basically, the main periodic table is usually divided into two parts. The main periodic table includes those elements from the sublevels S up to D. Those are the ones that are held in the main periodic table. Are we together up to there?
Yes.
This kind of a sub-periodic table takes into consideration those elements that are known that also have an F sublevel in their ground state, the lanthanide and actinide. Are you together?
Yes.
So, because in the main periodic table includes elements with S, P, and D sublevel. Now, the first two groups are those whose outermost electrons are in the S. Then here at the middle, 10 elements are those whose outermost electrons are in the D. So S has only 2 electrons. So those are 2 periods, isn't it? Groups, right?
Mhm.
D has
Yes.
10. D has 10 electrons. So those are 10 elements, right?
Yes.
P has 6. So 2 plus 10, 12. Then you add 6. Those are 18, right?
Yes.
And that is why the main periodic table has up to 18 groups, right?
Yes.
Yes.
And that one is clearer, isn't it?
Yes.
But note that usually the trend for those elements that are taking the D and have the outermost electron in the D sublevel usually does not align with those ones that only have P and S and P. So usually we label those whose outermost electrons are either in S or P as elements in period A. And the first column represents group 1. And when we only want to deal with those with S and P, we say it is group 1A. So the second one is 2A, group 2. The one usually when we are talking about the 8 groups, usually we are talking about the A group. Then we have group 3A, group 4A up to group 8A. Of course, group 8A is where we have what we call the noble gases with a full p orbital and no other electrons that are unshared, right?
Yes.
Yes.
So I don't think there's anything else I said about the periodic table. So is it clear now for the one who was asking? Because now that is where now I went to the threads.
Yes, it's okay now, Daktari. Asante.
So basically, this is the upper part of the periodic table, the main periodic table. So let me go back to the threads. So I was using this to explain the thread in terms of atomic radius. That as you go down a group, each step down the group increases an extra orbital, an extra principal quantum level, meaning increases the distance of the outermost electron from the nucleus to the orbital it is to the shell it is occupying, right?
Yes.
And so we are saying that distance from a nucleus to the outermost electron from the nucleus is what we call the atomic radius.
Radius.
Right? And I was saying practically it is not possible to take an atom, a single atom, and then you measure the atomic radius. So in practical terms, the way the atomic radius, the technique that the atomic radius that is used to determine the atomic radius is electronic X-ray mapping, which is able to map the distance from the nucleus of one atom to that of the neighboring atom. So I was saying that there are two types of atoms, of elements. Those that are molecular, those that usually have their atoms bonded to one another through covalent bonding. Those are the molecular atoms. For example, oxygen, nitrogen, chlorine, halogens. So that is basically groups 5 to group 5A to group 7A. Usually they exist as the atomic molecules, isn't it? Oxygen exists mostly as O2, nitrogen as N2, fluorine as F2, chlorine as Cl2, isn't it?
Yes.
Yes.
So we are saying that what you can be able to take using what can be physically determined is the distance between the nucleus of one atom and that of a neighboring atom in those molecular molecules. And that if you get that distance, the way that is drawn here, then you know that one. If you do, that one is like the diameter, isn't it? That would
Yes.
give a diameter because it is 2 times the radius, right? So the radius, then we determine the radius by dividing the distance by 2. Are we together? So for example, here they are showing that the internuclear distance has been determined to be 1 at 266 p.m. So the atomic radius is half of that. That is why it is written 1:33 p.m. Are you together?
Yes.
If, for example, that one is for molecular compounds. If, for example, you are talking about metals, metals usually exist in crystalline form, isn't it? In a solid, right?
Yes.
So what you can do is to get the distance between the radius in their crystalline form, and then you divide between the nucleus of two bordering atoms, and then you determine half the distance as the atomic radius. So that is how it is determined. And we are saying that the trend is such because we are interested in the trend. This one is just for purpose of understanding. The trend is such that as you go down the group, the atomic radius increases. That is a general concept because the outermost orbital increases, right? I think that one is very
Yes.
easy to understand. Yeah.
Yes.
That is why in this representation, you can look at the shapes drawn as, forget about the numbers. Okay, they are giving the atomic radius in terms of PM, but forget about the numbers. Look at the pictures themselves. What the pictures are showing is that the circle is increasing down the group, isn't it?
Yes.
Yes.
So basically, the pictures are trying to show you that the atomic radius increases down the group, right?
The group.
Look at the representation. Now, we're trying to use a very simple technique, what you can see, what you can figure out. Look at the trend across the period. For example, look at the trend across period 2, where we have starting from lithium. Forget about hydrogen and helium. So what can you observe?
Decreasing a lot.
The atomic radius
Isn't it?
increases.
So
The period.
what is showing is that the atomic radius is decreasing across the period, right?
Yes.
Yes.
So now the question, the first part of the atomic radius increasing down the group is very easy to understand, right?
Yes.
Now,
Yes.
why is the trend of atomic radius such that, but you notice on something else, although, and the decrease is from group 1 to group 7. Notice that. When you go to group 8, there is slight increase, isn't it?
Yes.
Yes.
Yeah. So that is also something you should note. But let us first of all talk about group 1 up to group 7. So why is that trend as such? So just a moment, I write something. I'm unmuted now. Okay, I'm back. Are you there?
Yes.
Yes.
Yes, we are there,
So,
Daktari.
we wanted to explain why, right?
Yes.
Why does the atomic radius? So this one explains the first part, which we have already understood very easily, about increasing. Now, so we are asking the question, why does this happen? As you go from left to right, the atomic radius decreases, isn't it?
Yes.
So here is where we try to. So as you go from left to right, what is happening? You remain in the same principal quantum level, right? So the electrons are being added to the same main orbital, right?
Yes.
But you are also increasing, for every increment of an electron, you're also increasing a proton, isn't it? In the nucleus, isn't it?
Yes.
Yes.
So when you add a proton in the nucleus, what happens is that you increase the pull towards the nucleus, isn't it?
Yes.
But when you also add an electron, there is also electrons themselves repel one another. So there is also electronic repulsion, right?
Yes.
Now, what is there is that let me go. What is there is that usually when you increase an electron in the same outermost shell, it does not cover those other electrons in the same principal quantum level because you're adding it sideways, not in front of those other electrons, isn't it? See, if you look at these pictures, we are trying to show that the outermost electrons are shielded from the nuclear pool by the inner electrons, isn't it?
Yes.
So basically what happens is that even though you're adding an electron to the same principal quantum level, it is not shielding the other electrons that are already in that outermost level, but it is being shielded by the inner quantum level. So the effective nuclear attraction is usually based on the number of electrons, of protons above the number of electrons in the inner shells. So for example, in chlorine, which is atomic number 17, the inner shells of electrons have 10 electrons. So while the outer shell has 7 electrons, but those 10 electrons shoot the outer shell electrons. And therefore they prevent, if we say that one electron stops one nucleus, one proton, then they stop 10 protons from attracting the outermost electrons because they neutralize one another, them. But the remaining 7 protons that are added as you go to chlorine are not shielded by anything. So therefore, there is a net of positive 10 that is attracting the outermost electrons. And although you increase the electrons, you increase the repulsion of electrons, the net repulsion for electrons that are in the same principal quantum level is retro compared to the net attraction in the nucleus. So basically, when you are moving across the period, we say that, so when you are moving across the period, you have greater proton pouring power as you move across the period. So the net pull per electron increases across the period, and that is why the atomic radius decreases, because those electrons are getting more and more attracted towards the nucleus because of unprotected protons. Are we together?
Yes.
Yes.
Although there will be some slight increase in a repulsion of electrons, the net pull by protons is more than the repulsion, and therefore the electrons tend to be brought closer. The orbital is, or the principal quantum level is tends to be squeezed towards the nucleus, and therefore the atomic radius decreases. So that is one trade of the atomic radius. So basically, we can conclude that when it comes to the atomic radius, generally, a trade is a general observation. Generally, as we go down the group, the atomic radius increases. As we go across the period, the atomic radius decreases. However, as we go to from group 6, from group 7 to group 8, when you go to the noble gases, there is a slight increment in the atomic radius. Why? Basically, that can only be explained by the extra stability that is obtained from a complete outermost principal quantum level. That stability tends to counter the or to give the electrons more resistance to the nuclear pool, and therefore either the atomic radius remain almost the same or increases slightly. So that is an abnormality in that trend. So again, so here we have a representation of elements across a period. That is period 2. You can see from beryllium, lithium, beryllium, nitrogen, oxygen, fluorine, and neon. Now, the ones that are shaded in purple are what we can call metallic elements, while the others are the molecular elements, elements that usually bond by sharing of electrons. The ones in purple are those that usually bond by loss of electrons. Among the molecular elements, when they bond with group 1 with elements in purple, usually they form ions. And we shall also talk about that thread. So this one we are talking about, when we say go across a row, we are talking about a period. So here is a representation. For example, chlorine and potassium are in the same period. Potassium is in group 1 to the left. It is here being shown that it has a larger radius than chlorine, and this is because of the effective nuclear charge. Nuclear attraction in potassium is less than the effective nuclear attraction in chlorine. So then when it comes to effective nuclear attraction, probably it is worth noting that for hydrogen and helium, the outermost electrons are in a principal quantum level that is next directly to the nucleus. And therefore, for hydrogen and helium, the issue of electronic shield, electronic shield, the shield that electrons have towards the outermost electron does not exist. And in hydrogen and helium, the outermost electrons get the maximum attraction to the nucleus, to their nucleus. Now, basically, this one is just talking about the same thing. It is telling you that for those elements with very, very many principal quantum level, so that the outermost electrons are very far from the nucleus, there is very heavy shielding in the outermost electrons, meaning that the net nuclear attraction to the outermost electron is very minimal. For example, in group 1, francium. Francium is at the bottom of group 1. It has 1, 2, 3, 4, 5, 6 principal quantum levels before the 7th principal quantum level outermost electron, you go to the 7th principal quantum electron. So it means that the outermost electron in francium is so shielded from the nucleus that the net attraction to that electron is very minimal. So what does that mean? It means that that electron can easily be lost, isn't it? And that is why as you go down the group, the ease of losing an electron increases because the outermost electron have very minimal attraction to the nucleus. So then we can talk about ionization energy. And what is ionization energy? Ionization energy is the amount of energy required to remove a valence electron. That is, when you say a valence electron, we are talking about the outermost electron from the space of nuclear attraction, so that it is no longer feels the attraction to the nucleus. So it is free. It is no longer now under the attraction of the specific nucleus. So atomic amount ionization energy is the energy required to remove a valence electron from an atom in gas phase, and that is when the atom is in gaseous phase, so that that electron is not subject to attraction by another nucleus, apart from the atom from which it is held. Now, the energy required to remove the first electron is what we call the first ionization energy. Now, once you remove that electron, if you want to remove another electron, a second one, then that one, the amount of energy now you require to remove the second electron once the first has been removed is what we call the second ionization energy, and so forth. So you say that valence, so those elements, generally, let's say what we are showing here is that those elements that have very many principal quantum level. The outermost electrons are very far from the nucleus, and that is where we are comparing, for example, lithium and cesium. Cesium is smaller than francium, but now cesium and lithium are in group 1. But you can see that the outermost electron in cesium is very far from the nucleus, and therefore the effective nuclear attraction to that electron is very small, and therefore the amount of energy required to remove that electron is minimum compared to that of lithium. And therefore you find that the first ionization energy in cesium will be much lower than the first ionization energy in lithium.
unaweza rudia, you can repeat that.
Okay, it's a very simple concept. Look at, now this diagrammatic representation. They may not be in any real ratios, but just a pictorial representation. You can see the atom lithium, isn't it?
Yes.
Very small, right?
Yes.
The outermost electron in lithium is very near the nucleus, isn't it? Because it only has two quantum levels, principal quantum levels, right? So the outermost electron in lithium has very minimum shielding by the inner electrons, right? And also it's very near the nucleus, so the effective nuclear attraction is also real, right?
Yes.
When you go to cesium, the outermost electron is very far from the nucleus, right?
Yes.
So, and also it is very much shielded by the inner electrons, right? You know, they are shielding because they are themselves being attracted to the nucleus, right?
Yes.
So in that case, cesium, the outermost electron, has very minimum attraction to the nucleus. It is very minimally attracted to the nucleus, right?
Yes.
So it's like, for example, if you have a magnet, probably if you have a magnet and a metal that it can attract, the nearer it is to the magnet, the more it will be attracted. It can easily it can move towards that magnet. But if it is far away, then the effective magnetic pull to that object reduces, isn't it?
Yes.
So in that case, it is easy to remove, for example, a blade by pulling, for example, with a string that is far from the magnet than the one that is nearer the magnet, isn't it?
Yes.
So, so in that case, it is easier to remove an electron from cesium than it is from lithium, right?
Yes.
So the energy required to remove an electron from cesium is minimal compared to that in lithium. Therefore, and that energy is what we are calling the ionization energy. So the ionization energy in cesium is much lower than the ionization energy in cesium. Right?
Lithium.
So that is the point. So on the opposite consideration is the energy to attract electrons from outside the sphere of an atom so that they now become part of that atom. That is electronegativity. Electronegativity is the ability to attract, of an atom to attract electrons that were free from that atom. Now, what are the nucleus of an atom? The easier an electron outside the atom would be nearer the nucleus, isn't it? Let me try to go to a pictorial. Let me see whether. You see, let's just try to look for a good representation that can explain what. So let us use this as a representation. As you move across the period, the atomic radius decreases, isn't it?
Yes.
So the atom, the outermost electrons are nearer the nucleus, isn't it?
Yes.
Yes.
It means that even an electron that is moving outside the sphere of the atom, it can come very close to the nucleus, isn't it?
Yes.
And in that case, an electron that is outside the sphere of this atom can easily be attracted when the radius is smaller than when you have a very big radius, so that it is operating from very far from the nucleus, right? Because the nearer the nucleus, the more force that it is having outside that sphere, right?
Yes.
And therefore, the energy required to attract an electron, that is minimum. And the smaller the amount of energy required, or the greater the force that is attracting external electrons, the more electronegative an element it is. So we say that the smaller the nucleus of an atom, the more electronegative it is. So the smallest atoms have the greatest electronegativity. And so, because the size of atomic radius increases down the group, but decreases across the period, it means that up the group and across the period, the electronegativity increases. So the element, let me go to the picture, the main table. So if you look at these elements, which are the smallest elements? They are the ones in period 2 and at the top of and period 2 groups 6 and 7, and particularly group 7, because as you move across the period, the atomic radius is decreasing, isn't it?
Yes.
It means that as you move across the period, because the atomic radius is decreasing, the ability of the nucleus to attract electrons towards it from outside increases, and therefore electronegativity increases. So electronegativity increases across the period. But as you move down the group, even within the same, even in group 7, as you move down the group, the atomic radius increases and electronegativity decreases, isn't it? The ability to attract electrons outside the nucleus. Are we together?
Yes.
Yes.
So basically, down the group, electropositivity increases. That is the ability to give away electrons. Up the group, electronegativity increases, the ability to attract electrons, isn't it?
Yes.
Across the period, electronegativity increases. But down the group, electronegativity decreases, right?
Yes.
So those are the trends. Now, it means that in that kind of an argument, it means that those elements in group 1 and 2 usually have more electropositivity than electronegativity. They have more ability to lose electrons than to attract electrons. And that is usually why they react by losing electrons. But more important is to note that that strength of ability to lose electrons, what we can call electropositivity, increases down the group. And therefore, when and those elements in groups 1 and 2 usually have, just a moment. So those elements in group 1 and 2 usually need to, all elements, let me just put it this way, all elements usually try to achieve a full outermost electronic configuration. And how can they achieve a full outermost electronic configuration? It is either by losing electrons, if they have a few electrons, or by gaining electrons, if they only need a few electrons to gain a few electrons in the outermost tail to achieve the noble gas configuration. Now, for those elements in group 1 and 2, they usually need to gain 6 or 7 electrons to achieve the noble gas configuration. Now, you know, once you try to add an electron to a nucleus, to an atom, the first, that is electronegativity, or the energy required to hold that electron. Once you add an extra electron, as you add electrons, the repulsion between electrons will go on increasing. So usually it is very difficult to add more than 2 electrons to an atom. I'm not saying it is impossible, but it's very difficult. So usually those elements in group 1 and 2, because they would require to add so many electrons to achieve the noble gas configuration, usually they don't, it is impossible to get that type of energy. So usually elements in group 1 and 2 achieve the noble gas configuration, that is the group 8 configuration of a full outermost orbital, by losing their outermost electrons, because usually they have only 1 or 2 electrons. Outside to elements that are attracting the electron. And that is, they lose electrons by what we call ionization energy. The ionization energy required to achieve that noble gas configuration is little. However, it is very difficult to have the energy to attract the high number of electrons required to achieve the noble gas configuration. So they form ions by loss of 1 or 2 electrons, and therefore they create electropositive elements. Now, that ability to lose electrons, to achieve the noble gas configuration is an indication of metallic character. Now, as you move down the group, the ease of loss of electrons increases. So it becomes more easier because the energy required is small. And therefore, the reactivity of groups 1 and 2 elements is usually increasing down the group, because they react by loss of electrons. Now, for elements in group 6 and 7, usually they achieve the noble gas configuration by attracting 1 or 2 electrons to achieve the noble gas configuration. Now, the smaller the atom is, the easier it can attract those electrons. So basically, group 6 and 7 achieve the noble gas configuration through attraction of electrons. And because the ease of attracting electrons decreases down the group, the more active group 6 and 7 elements are those that are smaller, and therefore they are those at the top of the group. So for example, in group 7, fluorine is the most electronegative element and the most reactive. In group 6, oxygen is the most electronegative element and the most reactive, and the reactivity decreases down the group. So, trend, electronegativity trend is that it is minimum in the group 1 at the lowest point, and is maximum in group 7 at fluorine. So group 1 and 2 elements, those elements that form compound by rows of electrons, are usually referred to as metals. And they are judged by the ease with which they lose their electrons.
They are the losers.
Yeah, they lose electrons. So
They lose ni zile bujuju.
Nilimalizia na skati yangu ile.
this
Mute.
so group 1 and 2 elements, because as you go down the group, the easier it is to lose electrons, their reactivity increases down the group. But when it comes to group 6 and 7 elements, which are supposed to react by gain of electrons, the ease of gain of electrons decreases down the group. So the upper ones are the most reactive. So metals are reactivity increases down the group. Non-metals reactivity, that is chlorine and fluorine, increases up the group or decreases down the group. So that is those are some of the major trends that we are interested in. Now, so we are saying group 1 and 2 elements, we call them metals. They form positive ions by rows of electrons. And they give those electrons to group 6 and 7 elements, which can gain 1 or 2 electrons. So usually when group 1 and 2 elements react with group 6 and 7 elements, they form ionic compounds because one loses electron, therefore gains positive charge. The other one accepts those electrons, gains positive charge, and they electrostatically attract one another to form ions. Now, for the elements in the middle of the periodic table, that is carbon, group 5, group 3, 4, and 5. Let me go to the periodic table. Now, if we use this periodic table, we are saying that these elements, we can ignore hydrogen in group 1 and 2, usually achieve the noble gas configuration by losing their 1 or 2 electrons in the outermost principal quantum level. And those electrons are usually taken by these elements either down the fluorine or down the oxygen, which only require 1 or 2 electrons to achieve a noble gas configuration and form negative ion. So these ones form, the ones 1 and 2 form positive ions, 6 and 7 form negative ions. And the positive ions attract the negative ions, they form ionic compounds. Now for the elements 3, 4, and 5, that is elements in group of boron, carbon, and nitrogen, to achieve the noble gas configuration, they will need to either accept 3 or more electrons or lose 3 or more electrons, where the energy for such transformation is very high, and therefore none of the possibility usually happens. Usually those elements do not lose or gain electrons. They usually form their compounds by sharing their outermost electrons. So they form what we call molecular compounds. Are you together?
Yes.
Yes.
And I think for that and for the purpose of generally understanding the periodic table, today we will stop there. So the rest of the information is just showing what happens when they gain or lose electrons. I think, so basically here we are showing that, for example, chlorine can achieve the noble gas configuration by gaining electrons. And here, what we are trying to show here is that when chlorine gains electron, because you have added an extra electron to a cell that already had electrons, they will repel one another and the radius will increase. So when you add an electron to an atom, the radius increases. Let me go back and see whether we have a rows of electron. If an element, for example, lithium, loses its outermost electron, now it means that it no longer has an electron in principal quantum shell number 2, and therefore the radius decreases. So for metals, they form positive ions by rows of electrons, and the ions, which we call cations, are smaller than the parent atoms. For the anions, that is, those elements that achieve the noble gas configuration by gaining an electron, they form anions, and the anions have a radius that is greater than the normal atom. So that is also a trend you can note. So unless there are any issues, I think I'll stop today's lesson there so that you can be able to go through. I think I've posted this one, or I'll post. So there are a number of people who have raised that. Sylvester?
Well, Daktari, I wanted to ask about the structures of the atoms, which I can see the levels, where you are drawing the levels. I don't know whether I will be right. The way you are arranging the electrons from the nucleus outwards.
Yes.
Is that one? So how do we arrange them? Help me understand.
Okay, this is what I'm giving here is a pictorial representation. Actually, let me try to. What we are giving is a pictorial representation. Let me try to. What we are giving is pictorial. It is not what you can use. You can use that one as a symbol, but when we are told to give the electronic information, what we are doing here is to give a picture so that you can understand. Otherwise, when we talk about electronic configuration at this level, I expect you to give me 1s1, 1s2, 2s2, 2p. But because of course, even when we give this pictorial diagram, usually this is just a symbolic representation. So what the electrons have been represented here is not an electronic configuration, just to show that there are electrons in inner shells that are shielding the electrons in the outer shell. Otherwise, an energy electronic configuration, you have to give the electron, the principal quantum level, the sublevel, and the number of electrons. So I'm not telling you that you give a representation of electrons this way. This is a symbolic way of trying to explain my point. Is that clear?
Thank you so much, Daktari. It's very clear.
So this is not any scientific representation.
Thank you so much.
So, Benson Beja.
Yes, Daktari. I want to commend you for the good presentation. I really
Yes, I can hear you.
giving me.
So
I was just requesting you to post
yes,
the modules that you are reaching.
I have posted. I don't know.
Oh, I
If
was
you go
on.
to discussion, if you go to the e-learning site, and I think you can ask the others, I think they have seen. you go to the e-learning site, you go to discussion, you go to general discussion, you get the notes. Some of the notes I've already given, and the module notes. Are we together?
Thank you, Dr.
Jurie Karemi. Jurie Karemi.
Good evening, Dr. You are to share the Word documents, the module in Word.
Have you gone to the e-learning site?
Well, I have not checked the last 3 days.
No,
You've already posted it?
Not in the last 3 days. It has been there for some time. If you go
yes,
to
the PDF one. I am saying the Word.
Yes.
The PDF has been there, but I was unable to print. Normally, I print because of my eyesight.
Oh,
it's
no, I'm
really
saying
poor.
I
am not
have posted there's no Word document. I think check the Word. Have you checked? And there's no Word document.
Yes, it's PDF.
It's PDF.
It's Word. It's Word.
I have asked. So why? Let me ask. Go to your WhatsApp. Ask those people who are able to get the Word document to post to your WhatsApp, and then you can download from there.
Okay, thank you.
That would be an easier route. So that is Jurie Karemi. So Bete Shemtai. Betty? You had his list, but or probably you forgot what. Musioki Muru. Musioki. I think those ones have raised their hand unknowingly. So have a good night.
When are we having the next lesson?
Just
yes. Aya, watu walale salama basi.
Pia tu nini bwana?
Mwende